Welcome to this session on CCNA tutorial, Network Fundamentals. This video is aligned with Cisco's official CCNA 200-301 exam blueprint and is designed to guide you step-by-step towards certification success. In this lesson, we cover Section 1.12, Virtualization Fundamentals. We're going to explore the technologies that power modern data centers and cloud environments. We'll start by looking at what virtualization actually is, then move through hypervisors, virtual machines, containers, and how virtual networking works behind the scenes. We'll also cover virtual switches, virtual NICs, NFV, VRFs, virtual storage, and the different cloud service models. By the end of this section, you'll have a clear picture of how today's virtualized networks operate and why virtualization is such a critical foundation for modern IT. Virtualization is all about taking a single physical machine and breaking it into multiple independent virtual machines that share the same hardware. Instead of dedicating one server to one workload, you can run many workloads side by side, each inside its own VM with its own operating system and resources. This dramatically improves efficiency and reduces the amount of physical equipment you need. It also gives you flexibility. VMs can be moved, copied, backed up, or restored easily because they exist as software-based instances rather than physical boxes. There are a few different ways virtualization can be implemented behind the scenes. Full virtualization is the most common, where the guest OS thinks it's running on real hardware, even though everything is emulated by the hypervisor. Partial virtualization exposes some hardware directly, reducing overhead but requiring some OS awareness. And para-virtualization takes that a step further by allowing the OS to communicate directly with the hypervisor using optimized calls. These different approaches give you different trade-offs between performance, compatibility, and efficiency. A hypervisor is the core component that makes virtualization possible. It sits directly on the hardware or on top of a host operating system, and it creates and manages virtual machines. It allocates CPU, memory, storage, and network resources to each VM and ensures that each one remains isolated from the others. The hypervisor also gives you features like snapshots, cloning, and live migration. Essentially, the hypervisor is responsible for coordinating all of the virtual hardware and keeping your environment stable and efficient. There are two categories of hypervisors. Type 1, or bare metal hypervisors like VMware ESXi and Microsoft Hyper-V Server, run directly on the hardware and are used in production data centers because they offer high performance and stability. Type 2 hypervisors sit on top of a host operating system like VirtualBox or VMware Workstation. These are perfect for labs, testing, and development. Both types support virtualization, but they're used in different environments depending on whether you need enterprise-grade performance or a simple, flexible test setup. A virtual machine is basically a full computer running inside another computer. It has its own operating system, applications, virtual CPU, RAM, storage, and network interfaces. From the VM's perspective, everything looks like dedicated hardware, but in reality, the hypervisor provides all the virtual components. VMs are completely isolated from each other, which makes them secure and stable. And because a VM is stored as a set of files, it's incredibly easy to move, back up, copy, or restore, making virtualization far more flexible than physical servers. Containers are a lighter-weight alternative to virtual machines. Instead of running an entire operating system for each instance, containers share the host's OS kernel, but keep applications isolated from each other. They start very quickly, use fewer resources, and are ideal for cloud-native environments where you need to deploy and scale applications rapidly. Tools like Docker and Kubernetes make it easy to package code with everything it needs and run it consistently across different environments. Containers and VMs both provide isolation, but they do so in different ways. VMs virtualize hardware and run full operating systems, which gives strong isolation and compatibility with almost any OS. Containers, on the other hand, virtualize only the application environment, so they're much smaller and faster to start. VMs are great for infrastructure and long-running workloads, while containers excel in modern application development, microservices, and environments where frequent updates or rapid scaling are required. Most organizations use both technologies depending on the workload. Virtual networking provides all the connectivity needed within a virtualized environment. The hypervisor creates virtual switches, virtual NICs, port groups, and uplinks so virtual machines can communicate just like they would on a physical network. You can assign VLANs, apply policies, isolate workloads, and control traffic, all from software. This makes networking inside a virtual environment incredibly flexible, scalable, and easy to modify without touching physical hardware. A virtual switch works just like a physical Ethernet switch, except it's entirely software-defined. It connects VMs to each other and to the external network through physical uplinks. It understands MAC addresses, supports VLAN tagging and trunking, and applies security or traffic policies based on the port group configuration. Because it's virtual, you can instantly reconfigure, clone, or expand your switching environment. Popular implementations include VMware vSwitch, VMware Distributed Switch, Hyper-V Virtual Switch, and Open vSwitch. A virtual NIC is the network interface a VM uses to communicate. It behaves like a physical NIC, complete with its own MAC address and VLAN tagging capabilities, but it's created and managed by the hypervisor. You can connect a VNIC to different port groups, add additional VNICs for multi-homing, or reconfigure them without restarting the VM. Modern virtual NICs, such as VMXNet 3, are optimized for performance and integrate tightly with the hypervisor's networking stack. NFV moves traditional network appliances like routers, firewalls, and load balancers into software that runs on standard servers. Instead of buying dedicated hardware, you deploy a virtual router or firewall as a VM or container. This approach is incredibly flexible and cost-effective because you can scale services up or down quickly, deploy them wherever needed, and automate their configuration. NFV is widely used in cloud environments, service provider networks, and modern enterprise data centers. A VRF allows a single router or switch to maintain multiple independent routing tables at the same time. Each VRF acts like a separate virtual router with its own interfaces and routes. This is extremely useful for segmenting networks, supporting multiple customers, or handling overlapping IP address ranges. VRFs are essential in MPLS networks, multi-tenant environments, and large enterprises where traffic separation and security are critical. Virtual storage abstracts multiple physical disks and storage systems into logical storage pools that virtual machines can use. Instead of being tied to a specific physical disk, a VM sees a virtual disk located on shared storage. This enables high availability, live migration, and clustering because VMs can run on different hosts while accessing the same data store. Virtual storage also supports thin provisioning, snapshots, and replication, features that make management easier and storage usage more efficient. ASAN provides block-level storage over dedicated high-performance networks like Fibre Channel. To the server, SAN storage looks like a local disk and is ideal for demanding workloads like databases and virtualization clusters. NAS provides file-level storage over standard Ethernet using protocols like NFS or SMB, making it perfect for file sharing, backups, and user directories. Both play important roles, but SAN is optimized for performance and low latency, while NAS focuses on accessibility and simplicity. Cloud computing relies heavily on virtualization. Cloud providers pool vast amounts of compute, storage, and networking resources and use virtualization to carve them up into on-demand services. This makes cloud environments scalable, automated, and highly resilient. When you spin up a VM on AWS, Azure, or Google Cloud, virtualization is working behind the scenes to allocate resources, isolate workloads, and ensure high availability. Virtualization is essentially the engine that powers the cloud. IaaS gives you virtual machines, virtual networks, and scalable storage directly from the cloud. You control the operating systems, applications, and security settings, while the provider manages the underlying hardware and hypervisors. This model is perfect for lift and shift migrations, running servers without owning physical hardware, and building flexible, scalable environments. Common examples include AWS EC2, Azure Virtual Machines, and Google Compute Engine. PaaS provides a fully managed platform where you can build and deploy applications without worrying about the underlying servers. The cloud provider handles the operating system, runtime, scaling, security updates, pretty much everything except your code and data. It's ideal for developers who want to focus on building applications rather than managing infrastructure. Examples include Azure App Service, Google App Engine, and serverless offerings like AWS Lambda. SaaS delivers complete applications over the internet, fully managed by the provider. You don't manage servers, storage, or even the platform. Everything is handled for you. Users just log in and start working. SaaS covers things like email, collaboration tools, CRM systems, and productivity apps. Popular examples include Microsoft 365, Google Workspace, Salesforce, Zoom, and Slack. It's the simplest cloud model from a management perspective. In this section, we explored the full virtualization ecosystem, from hypervisors and virtual machines to containers, virtual networking, NFV, VRFs, storage virtualization, and cloud models like IaaS, PaaS, and SaaS. All of these technologies play a key role in modern data centers and cloud environments. Understanding how they fit together will make the next modules on switching, routing, and network services much easier to understand. Virtualization is truly the foundation of today's IT infrastructure. Before moving on, take a quiz to test your understanding. Quizzes, summaries, and slides are available on ccna.academy. If you have any questions, leave a comment below, and I'll be happy to help. Up next, we're moving into switching concepts. We'll look at how switches learn MAC addresses, how they forward and flood frames, and how the MAC address table is built and maintained. This section sets the stage for understanding how Ethernet switching actually works in real networks.